So let's start. And hello everyone. You haven't seen me before. I'm Zining. I'm one of the 3 co-instructors here at 401. And for this lecture and the lecture next Monday, I will present the entropy and decisions. And after that, another co-instructor, Raid, will present materials including hidden Markov model and machine translation. And after that, I will come back to present the materials about, for example, automatic speech recognition and natural language understanding. And towards the end of the semester, I will present a lecture about large language models, including ChatGPT. So in this lecture, we will talk about the entropy and decisions. This is a module that is usually less relevant to the natural language processing, but it is still a very important module because currently we are living in the world of information, and the amount of information is growing exponentially. There is the flooding information, and nowadays it has become more and more important to be able to navigate through and process those information. And this lecture we will describe the some basics of processing information. So you have probably heard on the newspapers about the misinformation and disinformation. Sometimes what you see on the social media consists of fake news. And these are type of information that you want to filter out. And on your cell phone or a laptop, there's usually the concept of storage, and they are described in megabytes, gigabytes. For example, many computers have 256 gigabytes of storage, and some have 512 gigabytes or 1 terabyte. These are actually the units of information. They describe how much information that can be stored in your computer or the cell phone hard drive. In a few slides, I will describe why byte is the unit for information, and gigabyte is 10 to the power of like some unit of the it's some multiplicities of the bit. And in the next lecture, next Monday, I will talk about decisions. So the decisions part will involve some statistical tools to help you solidify your decisions. So for example, if you see that, if you have a friend named Elon, and you want to decide whether his tweets, average length of his tweets are longer than 100 words, then you can use hypothesis testing and t-test to solidify the decisions. So that when you say that my friend Elon's tweet is longer than 100 words, then you will be backed up by the statistical test. You can say, for example, after this test, the p-value is less than 0.05, so that I can have a lot of confidence to say that his tweet is longer than 100 words. But we will talk about that in the next Monday. For now, let's get into some basics of information theory, starting from entropy. Imagine that someone whose name is Darth Vader, he's about to say either yes or no with equal probability. So before hearing what he says, there's no idea what he will say. So in this situation, there's a certain amount of uncertainty. And the uncertainty could be removed by the observation of this event. And observing this event gives you information. And this information removes uncertainty. So information removes uncertainty. And a lack of information is, in other words, uncertainty. And we can describe the quantity of, this information, of the event that is brought into removing the uncertainty of the unknown. And let's try to describe the units of the information. So 1 bit of information is It's basically an observation. And one of the most simple type of observation is that you observe whether he says yes or no. So after observing whether he says yes or no, this bit of uncertainty is gone. So you get one bit of information. So this is defined as one bit. So let's try to make this more formal. Before observing this event, there are half of the probability of either of the two options. But after that, only one of this case is observed. So you have one bit for an event that has probability of half of going towards either options. Imagine that in addition to that data, there's also a mirrored vast data. And you can observe that, and these two guys are independent. So they can either, any one of them can say either yes or no. And you're going to observe both dv and vd. So observing dv gives you one bit of information, and observing vd will also give you one bit. So observing both of them will give you 2 bits of information, right? And let's take a look at how many scenarios out there. So each of them can say either yes or no. So both of them can say yes, 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 no, no, yes, or no, no. So there are 4 possible scenarios. All of them have equal probabilities. So for the convenience, let's write them as 2 to the power of 2. So there are 4 scenarios. And observing the outcome of the 4 scenarios will give us 2 bits of information. So 2 bit is related to the observation of an event where each of the outcome have 1 over 2 to the power of 2 probability. So the amount of information that you observe is doubled when the inverse of the probability is squared. So there is a logarithm relationship between the amount of information and the inverse of the probability. So we can describe so let's try to relate the amount of information with the probability. So we know probability, and probability can be described by numbers. And the goal is to try to figure out a math equation to describe the amount of information. So there's definitely going to be a logarithm component in the amount of information, the equation. So let's just say I of x equals logarithm of inverse of p. In this way, when you square the p, you need to double the information I. And for convenience, and actually for historical reasons, the unit of logarithm is taken as 2 here. So you can also see, for example, in the machine learning literature, that people use logarithm of base e, the natural logarithm. But here, for to respect the history of the information theory, we are still using unit 2. And logarithm of 1 over p equals negative of logarithm of p. So you can also see that some people are writing this equation as negative of log of p. They are equivalent mathematically. So going back to the yes or no example, probability of yes and probability of no are all half. So the information contents that you observe that you get by observing the outcome no equals logarithm of 2 of 1 over probability of no, which is log of 1 over half, which is 1 bit. And as a side note, the negative log likelihood or logarithm of 1 over probability is also called surprisal. So this is the amount of surprise you observe when you observe this event. So if this event is very unlikely and you still observe it, then you will probably feel more surprised. This is described by this event having a higher surprisal number. So information is related to surprise. and it's also related to uncertainty. Information removes the uncertainty and introduces surprise. And to some extent, actually, surprise removes uncertainty. But we will talk about the meaning of those information quantities in some slides later. What if there are multiple outcomes? Imagine there are 6 outcomes other than 2 outcomes. So if Darth Vader is going to roll a fair die, then there are 6 outcomes, and each outcome has the probability of 1 over 6. How much information you observe are you going to observe when you see that, for example, the result is 6? We can plug in the equations and see that the information content is logarithm of 1 over probability of 6, which is 1 over 6, which is 2.58 bit. So there are more information when you observe an event which is less likely to happen. So this echoes the point I mentioned in the previous slide. So if the event is less likely to happen and you still observe it, then you're going to have more information. So one of the good things about this math formulation is that the property of, the information content can be additive. By additive, I mean that you can add up the information contents of multiple events and get the correct answer. So this requires that the events to be independent, like dv and vd. So in the case where vd says the same thing as dv, then it doesn't really make some difference when you observe dv versus you observe both dv and vd, right? Because if they are saying the same thing. But otherwise, if dv and vd are 2 independent persons and they make independent decisions, then the observation of both of them will give you twice as much information as observing only one. So the information is additive when the events are independent. You can check the math later. I don't want to go into the details. So essentially, the logarithm converts the multiplicities into additions. And if the events are independent, then you can multiply the probabilities to get a joint probability. And this multiplication can be converted into addition by the logarithm. So information can be additive is just a paraphrase of the joint probabilities of independent events can be factored out into multiplications. But if the events are not independent, you cannot just do this. I'll talk about that later. There are some other numbers that can describe how much these 2 events are dependent on each other. And when you know one event, how much uncertainty are you going to remove when you observe the outcome of the other event? So information is used to measure how much information. This kind of units are used to measure how much of information can be stored in computers. 1 gigabyte is 2 to the power of 10, is around 1,000 megabytes, and each megabyte is around 1,000 kilobytes, and each KB equals around 1,000 bytes, and each byte equals 8 bits. So this kind of conversions are. There are usually some people who ask, why not 1,000? Why use 2 to the power of 10, which is around 1,024? And I don't have a good answer, and as far as I can say, it's based on historical reasons. And the computer systems are all based on the binarizations. So if you have high voltage, it is a 1, otherwise it's a 0. And a binary system is much more convenient than for example, ternary system or a unit of 10. So let's get back to the information theory. The concept of random variable is a very important concept that is different from event. So usually many people mistake event to random variables, but event is a sample from a random variable. It's an observation. An event is deterministic, but a random variable is variable. It can be varied, and the value of the variable can be changed. So every time you observe a variable, you get an observation and you get a deterministic number, but you do not change the random variable, and the random variable still has intrinsic randomness out there. The intrinsic uncertainty in the random variable can be described by entropy, as I'll describe in a few slides. And the observation of the event brings you an amount of information. So let's say the random variable is Darth Vader saying something. And you observe he says something, and the observation is an event. And the random variable is the source of information, and the event is the output. So let's further take a look at some outcomes with unequal probabilities. So imagine that this die is not a fair die, and there are 0.7 probability that this is not rolling a fair die. This is describes the probability that Darth Vader is saying something, but in addition to saying yes and no, he can also say maybe, sure, dark side, or even destiny. And the probability of his saying no is 0.7, which is you are fairly certain that what he will say is going to be no. And when observing the output of Darth Vader saying one of the 6 outcomes, what is the average amount of information out there? So you can plug in the equations of information content and take the average, weighted by the probability of each scenario. And the resulting number is defined as entropy. The entropy is the expected gain of information you see from observing the event of a random variable. So this is expected over all the possible observations of this random variable. In the example of the previous slide, you need to take the expectation over all the 6 outcomes. So there's the probability of no times logarithm of 1 over no, plus the probability of yes times logarithm of 1 over yes, plus the probability of sure times logarithm of 1 over sure, and all of the other outcomes out there. You take the average and you get the entropy. So the entropy is defined towards a random variable. In order to compute the entropy, you need to take the average across all the possible events that can be emitted by the random variable. So this slide contains some computation examples. I'm not going to repeat the computation steps because it's boring. When you have time after classes, you can plug in your computers and see that and verify that these numbers describe the entropies of the 2 random variables. So you can see that the 1.5 is less than 2.58, 2.585. So when in the second random variable, there are there are actually more uncertainties out there. Because in the first random variable, you're almost certain that the outcome is going to be no. If you just say no, there are 0.7 probability that you're going to match what Darth Vader says. But in the second random variable, all the possible outcomes are equally unknown. So when observing one of the outcomes, on average, you're going to get more information. Let's plot the probabilities in a histogram. If the histogram is flatter, like rolling a fair die, then the distribution is flatter. And therefore, the entropy is higher because there's more uncertainties out there. And on the right-hand side, the distributions are more skewed towards the central point. And therefore, there are lower entropies. So low entropy corresponds to less uncertainty. Entropy has some bounds. The maximum of the entropy is the scenario where the random variable is the most the most chaotic. And what is the most chaotic distribution? It's the uniform distribution. So in that case, the entropy gets its maximum value. And the maximum value is log of m, where m is the number of choices. This can be also verified by Jensen-Shannon inequality. I'm not going to go into details of that inequality, but you can just take this as a fact. So the bounds, the upper bound on entropy of a random variable is reached when the probability distribution follows a uniform distribution. And on the other hand, the minimum of the entropy is reached when there's only one choice out there. So there's no uncertainty at all. And the entropy is going to be 0. So up to now, we have seen that entropy is the average amount of information provided by an observation of a random variable. And it is also the average amount of uncertainty you have before this observation. So this observation, on average, removes this amount of uncertainty. So this observation gives you this amount of information. And this is also the average amount of surprise you see during this observation. Additionally, entropy is the number of bits needed to communicate that random variable. So in the real world, both humans and computers are communicating. And during communicating, we're transmitting information. And the amount of information is quantified by bits. So in order to communicate the random variable to another person, you need to at least transmit this number of bits to the listener. And in the coding scheme, so in the coding theory, you can, for example, come up with some coding scheme that describes what happens in the random variable to the listener. And Shannon showed that no matter what coding scheme you come up with, you cannot be more efficient than a limit. And in this limit, you're transmitting h of s amount of information. If you're interested, yeah.
So we had that Darth Vader random variable with the 6 outcomes.
Yep.
I think it had like the entropy was 1.5 or something. So how would we, like bullet point number 4 there, how would you communicate the outcome of that random variable with, I mean, even if we ran it up to 2 2 bits, how would you communicate the outcome of a random variable with 6 possible outcomes? Like, what does that look like?
So if you communicate in natural language, which is a really inefficient method for communicating the outcome, you can just say there are 6 outcomes, and each of the outcomes have probability, let's say 0.7, 0.2, 0.1, something like that. And this string contains a lot of information. And in order to encode that string, you will need many bits. And my point is, practically, we will use a lot more bits than the edge of S.
Okay, so it's kind of like a loose lower bound. You can't necessarily communicate with exactly that many bits, but you can't beat it. You're probably going to be somewhere above it.
Yeah,
You might
yeah.
not actually even be able to equal it.
Yeah, yeah.
There might be a tighter lower bound.
Yes, yes. This bound is really hard to reach, and currently there are some communication technologies, like you have probably heard the terms 3G, 4G, 5G, and even 6G in the future. These types of communication technology involves very clever methods that approximate these efficiencies, and in order to communicate following that efficiency, some future technologies will probably be needed. But when communicating between humans, it's because we need natural language in order to understand. So we are. It's almost certain that humans will need to communicate at an efficiency that's much lower than that. So we will need a lot more number of bits to transmit the same random event. Question?
Yeah, so again, about the Darth Vader example where the probability of no is 0.7. So I just wanted to make sure that I understand correctly. So imagine we have this like Darth Vader who outputs a sequence of tokens with the given probabilities. And we want to assign a binary code for every token, not necessarily of fixed length, so different length for different tokens,
Yep.
in such a way that we encode his stream of conscious the most effectively. And then the average amount of bits per token will be like 1.5 something.
Yes, yes.
The right way to think about it.
Yes, you can use, for example, Huffman coding to do that. But Huffman coding is not included in the 401 syllabus this year. And yeah.
I'm sure that I understood like where exactly the entropy, this number manifests. Like the average amount of bits for the optimal coding of a stream of tokens under these probabilities.
Under some good assumptions, Huffman coding can reach this efficiency, but usually they cannot. So I highly recommend to check out the Huffman coding algorithm. So essentially they are assigning some. So if there are some characters that observe more frequently, then they assign some shorter codes to that collection of characters. And for those low frequency characters, you assign some longer code. So the average code length or the average number of bits that is needed to transmit that random variable is going to be very short. Yeah, but
on average,
yeah.
it will be specifically the entropy for the lower bound.
Yes, the lower bound is the entropy. Yeah.
Yes, thank you very much.
Yeah. Any other questions about entropy? Yeah. Because so this is as an aside, so it's not included in exam. And the reason why we cannot reach an efficiency that is better than h of s is that there is that amount of information, and you want to transmit that amount of information, so you cannot carry less than that amount of information. Otherwise, you lose some part of information. So in loose list communication, the coding efficiency cannot be lower than that. Yeah. So let's take a look at some other terms. Joint entropy, conditional entropy, mutual information, and cross entropy. There are some fancy combinations of the entropies. For example, the joint entropy is the entropy of multiple variables. So in this example, let's consider the two events. One describes the temperature and the other describes the moisture. So the temperature could be either hot, mild, or cold. And the wetness could be either dry or wet. And the two events are not independent of each other. And you can compute the entropy of W and the entropy of T following the numbers here. And these computation examples are left for sort of homeworks if you are interested in reinforcing the memory of the equations for entropy. Let's define the joint entropy as the average amount of information needed to specify multiple variables simultaneously. So the equation is very similar as the equation for defining entropy. But instead of using P of x, you use P of x and y. And the summation is going over both x and y. So this is average across all the possibilities. So we replace the univariate probability, P of x, with the joint probability, P of x and y. Any questions about joint probability and joint entropy? Great. So now let's continue to describe the conditional entropy. So actually this slide is still a computation example of joint entropy. You just plug in the numbers that can be queried from this table, and you get the joint entropy. So an observation is that this joint entropy is smaller than the sum of the two individual entropies. This is because the two variables, W and T, are not completely independent. So the randomness of both of these two events are slightly smaller than the sum of the randomness of the W and T together. And their difference is related to the mutual information of these two variables. I'll explain them in a few slides. So the two random variables, temperatures and wetness, have some dependencies to each other. So if we know exactly one variable, then there's less confusion about the other variable. And we can define the conditional entropy as the average amount of information needed to specify one variable when you know the other. So when you know that x equals the random variable large X equals small x, you can compute the entropy of y when you plug in the value of x, and you take this amount and take the average over all the possible value of x, you will get the conditional entropy of y. So the conditional entropy of y given x is average over all the possible values of x. So no matter what value of x is, once you know x, this conditional entropy describes the remaining uncertainty that you will need to remove in order to determine the value of y. Question?
Yeah, a question about the rightmost term, h of y given x equals small x.
Yes.
So basically, for every fixed small x, I look up a column in the table of joint probabilities. Then I have a distribution of y given this particular value of x. And this is the entropy of this exact distribution, right?
The value you are going to look up is marginal probability instead of the joint probability.
Yes, basically
Yeah.
a probability of y with a fixed x.
Yes, yes. So y, the probability of y given fixed x can be computed in exactly this slide. So the conditional probability is computed by the joint probability over the marginal probability. So yeah, actually you query both the joint probability and the marginal probability, and you divide them, and you get the conditional probability. So you take the conditional probability and plug in the equations and get the conditional entropy. So this is a computation example. So in the exam, there is always in every year there is going to be one question to compute the entropy, conditional entropy, joint entropy, and later the mutual information. And usually the location where most students make mistake is the conditional entropy. Usually some people will going to query the joint entropy instead of the joint probability instead of the conditional probability. So I want to emphasize that it is you need to query the conditional probability out there, and conditional probability is not immediately obvious, so you need to do this conversion. So after this conversion, these probabilities are ready for you to plug in the equations. So imagine that we want to query the conditional probability P of t given W. Then you specify the value of W and divide the number of the joint probabilities with the marginal probabilities of the value that you specify, which is 0.6 in the first row and 0.4 in the second row, to get the conditional probability. And then plug in the conditional probabilities to the equations. And after that, take the weighted average of these two terms to get the conditional entropy. Yeah, question?
Yeah, so will this intuitive understanding be correct? So basically, h of temperature given wetness means that on average, if I get to know the wetness, what remaining entropy is there for temperature?
Exactly.
And basically, in case when they are independent, where wetness doesn't communicate anything about temperature,
yes,
the entropy would be the same as just entropy for temperature.
Yes,
because
yes.
wetness doesn't help.
Yes. Yes, exactly. So when these two variables are independent, then knowing one of them does not reduce the uncertainty of the other. So in that case, the entropy, the conditional entropy of the other variable given this variable is still the entropy of that variable itself.
And is it true that conditional entropy is no greater than like regular one? H of t given W is not greater than H of t.
Yes. Exactly, and their difference is exactly a term that is called mutual information, and I'll describe that in the next slide.
Thank you.
Yeah. So, because the temperature and wetness are related to each other, and knowing one of them removes some uncertainty of knowing the other. And the point of this slide is to show that knowing the wetness tells us about something about the temperature, and here this slide shows another computation example that tries to show that knowing knowing the temperature can tell us something about the wetness as well. So you can compare the two numbers. So knowing the wetness tells us around 0.1345 bits about the temperature, and knowing the temperature tells us the exact same number, same number of bits about the wetness on average. So this is not a coincidence. This is because the two terms are the same. The two differences are the same terms. So this equals the mutual information between T and W, and same as this one. This also equals the mutual information between T and W. So the mutual information describes the average amount of information that is shared between those two variables. Intuitively, this is the amount of information that is reduced by knowing one, by knowing one of them when you query another. So the math equation is the expectation of logarithm of the joint probability divided by the marginalized probability. So in the case where x and y are independent of each other, then the joint probability could be factored out. It could be the numerator could be written to p of x times p of y. Then it cancels out with the denominator, and the mutual information will equal 0 if the two variables are independent. But otherwise, there are going to be some mutual informations between those two variables. And another common is that the value of mutual information does not really depend on the actual the actual values that these two random variables could take. It only depends on the probabilities that the random variables can go into each of the scenarios. So it could be, so the actual values could be the number of the number shown on the die when you roll a fair dice, in which case it's 1, 2, 3, 4, 5, 6. It could also be a string. It could be the words that are shouted out by Darth Vader. But we can still measure the amount of information between some random variables, and we can quantify the randomness using entropy. So one of the best things I like about information theory is that it can sort of describe the underlying mechanisms in the world. It can describe how much uncertainty out there in some random events. So some events might occur random to us, but behind those randomness, there are some numbers that we can quantify those randomness. And we can compare how much surprise are we going to be when we observe some event. And this slide shows a Venn diagram showing the relations between the entropy terms. So you can plug in the definitions of those terms and verify that the h of x and y, the joint entropy equals the entropy of x plus entropy of y minus the mutual information. And in the next two slides, I'm going to describe some terms that are used frequently in machine learning. So the information theory is currently very widely used in machine learning. And in this slide, I introduced the Kubeck-Leibler divergence. And this divergence measures the difference between two probability distributions. So let's say the two distributions are P of x and Q of x. And KL is defined as the expectation over P times the logarithm of P divided by Q. So this divergence is always greater or equal to 0. And the equality is reached when P and Q, the two distributions, exactly match each other at every single value, at every single possible value of x. And also KL is asymmetrical, which means KL of P and Q is different from KL of Q and P. So the forward KL is different from the backward KL. Usually it's very hard to precisely know the KL divergence of two distributions because in the real world, the distributions are very complicated and we can only sample from the sources to get some observations and approximate the number of the probabilities. But once we know the exact value of P and Q, it will be relatively easy to compute the KL divergence. And KL is very frequently used in reinforcement learning, which is also not in the range of the CSE 401 exam. Actually, all of this slide is not in the exam. And this slide is also not in the exam. I'm just saying that in case you're interested. So cross entropy also measures the dissimilarity between two distributions. And it's used to measure how much does distribution Q differs from P. And in machine learning, they are using cross entropy to describe the situations where P and Q are both conditional probability distributions. And P of y given x is specified by the dataset themselves. And Q of y of given x is specified by for example, a deep neural network. And the cross entropy is very frequently used in machine learning because it has very nice math formulations when you take the gradient of this term. More details will be in the CSE 311. And as another side note, in machine learning, they use cross entropy in the base E, whereas in the CSE 401, we compute the entropy, conditional entropy, and mutual information in base 2 of the logarithm, of course. So as a summary of this lecture, by the end of this lecture, you should be able to describe what is random variable and random event. So you should be able to tell the difference between a variable and an event. A variable is random, whereas an event is an observation, and event is deterministic. And you should be able to write out how to compute entropy, joint entropy, and conditional entropy, and mutual information. And additionally, I hope you're familiar with the terms KL divergence and cross entropy. So if you have some feedbacks, feel free to scan this QR code and give some feedback. And this feedback form is anonymous. So I will appreciate if you give some feedbacks. And that's the end of this lecture. I'll see you on Monday.